Hi guys, in previous class we discussed about rolling friction. So rolling friction F suffix R is directly proportional to normal reaction force R, and rolling friction is inversely proportional to the radius of cylinder or wheel. So we got that rolling friction F suffix R which is equal to mu R, which is known as coefficient of rolling friction, times capital R upon little r. So this is the expression for rolling friction. So here mu R we define as coefficient of rolling friction. So today's class we will find which is easier. It means pulling an object is easier or pushing an object is easier. Right now you see, so a roller is using by a land roller. So he's applying force. She's applying a force in the forward direction. So this is the force direction. So this action we call as pushing a roller. So he needs to do work, and if you can take, right now he is pulling, so he is applying force in the upward direction. So he is applying force in the upward direction. So this action is known as pulling a roller. So to do the action, we need to do work and we need to apply force. So whatever it is, so we are going to find which action is easier, pulling a roller or pushing. So to find that, let us do a small diagrammatic representation for both pushing a roller and the same free body diagrammatic representation for pulling a roller. So the question comes like this: it is easier to pull a body than push it. So for that, so let me take a quick diagram. Suppose if I take a roller, so this circular roller which kept on the surface. So this is a horizontal surface of the ground. Now if I take pulling case, first I would like to take case pulling a roller. So it means we need to apply force. Suppose if I draw a roller handle, so this is handle of roller. So we need to apply force on the handle. So let this is the direction of force. So the direction of force which is right applied. So this is the direction of force. Now, if you represent the remaining forces, so the first, so the gravity which is acts in the downward direction. So this is the force which acts downward direction, which is mg. So this is the first force. And we know that there is force which always opposes the gravity. So that is normal reaction force. So this is opposing normal reaction force R. Okay. Now for a moment, if I delete this handle to represent very clearly, so this is the force direction. Now this force is making an angle theta. Suppose if I draw a coordinate axis at here, if I draw a coordinate axis, rough coordinate axis, now the force is making an angle theta with the horizontal. So this is theta, and if this is force, now we know that the force now resolve into components. So this component is F cos theta component, and upward force I can represent with that a small arrow, the force component along this direction, F cos theta. And one more component is acting vertically upwards, so this component is F sin theta. So this is F sin theta. Now apart of these forces, so here you can see the forces R and mg, normal action force, and two more forces, that is F cos theta and F sin theta. And very important force which till now did not draw, so that is friction force. Since the roller is moving, so it is having friction of kinetic friction. So I can represent this with very thick line so that we can see very clearly. So this is the friction force. We can represent that as F suffix k. So kinetic friction, F suffix k, which is acting opposite to the applied force. Now this is the corresponding diagram. So let us make it equal the sum of the forces. Now the only observable thing at here, the force F has two components. The applied force F has two components in the pulling case. One is horizontal component F cos theta, horizontal component, so that called as F cos theta. So this component help us to move forward. So it help to move forward. And the vertical component, the second component is vertical component. So this is F sin theta. So this is vertical components which acts in upward direction. And let us write the sum of the forces. Now, if you can make equal upward force equal to downward force. So in the upward direction the forces are, you are seeing two forces, that is normal action force plus one more force, the component of force F sin theta, which equal to the downward force equal to weight. I can take that mg as weight. So for a moment you can take this out and you can take this as called weight. Now let us write the friction force. So force of kinetic friction. Force of kinetic friction. So we know that F suffix k equal to mu suffix k times normal action force R. So from the above equation, if you can rewrite this equation in terms of R, so therefore R equal to weight minus F sin theta. Let me take as equation 1. Now this is equation 2. Substitute 1 in 2. So 1 in 2. So you get the expression for f suffix k. F suffix k equal to mu k of w minus f sine theta. So let it take as equation A. So this is the magnitude of the friction force. So this is the magnitude of the friction force in pulling action. So because friction force only gives whether which action is easier. If the friction force is less, then that action is easier. So finally I got that friction force which is acting in pulling a roller. Now let me take another case for pushing. Pushing a roller. So if I draw a quick diagram, suppose this is a roller. So this is kept on rolling on a surface. So this is surface. Now this time, so if I draw the handle for the pushing. So if I draw a handle for a moment, so this is the roller handle. Now the force which is acting along in this direction. So now, so this is the force which is acting towards to the roller. Now as usual, if you take the coordinate system at the center, so this is the imaginary coordinate system to find out the forces. Now this force, if you can extend, so that force is which is acting along in this direction. So I can represent with that. Now that is the force. Now for a moment, for the better understanding the diagram, if I remove the handle, just I remove the handle. Now let us try to put the forces. So if the force is making an angle theta, so this is the force F. Now the force having the components, that is F cos theta component along the horizontal, and the downward direction, this is F sin theta component. I can put the arrow marks. So if you can draw the force, so this is the force direction F cos theta component, and the vertically downward direction, so this is the F sin theta component. And apart of that, so normal action force which always acts perpendicular to the surface. So in this case, if I take normal action force as R dash to get the difference, and the downward force, we have one more downward force, that is nothing but weight. So the weight which is acting downward force direction. And apart of this, very important, so we need to represent the friction force. Now this case, the friction always acts down backward direction. So the friction force F suffix K. So these are the forces. Friction force F suffix K. I can take this as F suffix K dash. And R dash is the normal action force, and weight is which is acting downward direction, and the component of forces F cos theta and F sin theta. So you just understand the force making an angle pulling case and force making an angle in the pushing case. So because of the change in angle only differs everything. Now here, if you can represent the same thing, how the normal reaction force is balances with the downward forces. So we know that upward force is equal to downward force. So here upward forces are R dash is normal reaction force, which is equal to downward force. Two forces are there in the downward. One is F sine theta plus weight. Now if you can write the expression for force of kinetic friction, force of kinetic friction. So if I call that F dash K equal to mu K times R dash. Here the mu K is same because we are rolling on the same surface. So we can substitute F K dash equal to mu K times the R dash value here equal to F sine theta plus W. Let me equation B. So if you can closely observe these equations A and equations B, now equation A is like this. So that is I called Fk equal to mu K of W minus F sine theta. So this is equation A, or in the case of pulling. So notice the difference in the pulling case and pushing case. So this is the pulling and this represents pushing. So in the pulling case, the friction force F of K is having a negative of F sine theta. So this F sine theta is subtracting from this term. If this term is subtracting from weight, obviously F suffix K values decreases. So in the pulling case, the friction force is less. But if you can see in the pushing case, the F sine theta is added to weight. Here the plus is the component. F sine theta is added to weight. So now if you added this term, the total terms Fk dash is increasing. So we can say that Fk dash is greater than Fk. So the friction, kinetic friction in pushing is greater than pulling. So that we can say it is easy to pull. It is easy to pull than to push. What is the reason? Because kinetic friction. Kinetic friction in pulling is less than in pushing. So kinetic friction is only the reason to make the action is easy. So the kinetic friction is less in pulling action than in pushing action. So that's the reason we can say that it is easy to pull a body. It is easier to pull a body than push it. So this everything is a how the force components added. The way we pull the roller, the force components adds or subtracts. So that results the kinetic friction.